Okay, so the magnitude of V, we write double absolute value signs. And I'll tell you what this means in a moment. So the magnitude of lambda V is absolute value times the magnitude of V. So we can write the magnitude of lambda V. Constants can come outside of the magnitude. And we have lambda in absolute value times the magnitude of V. So what this means, right, is if V equals, let's just do there. Lambda is -1, so -1V. So that's going to have the exact same magnitude, and it's going to go in the opposite direction. That's that. If V, let's just keep the same V. It might be easier. Then 2 times V. Well, that's going to go in the same direction. This magnitude is considered 1, and the other magnitude would be 2. It would be 1, 2. There we go. Right, 1/2 V. Would be 1/2, and in the same direction. So that gives us another way of looking at the subtraction. Right, so let's just go this way. Let's let this be V. And there's W. So I know that when I add to V to get W, there's my subtraction, but notice 4/4, here's 4. This is also W, and I can do minus V. I can add minus V to it. So here's minus V. And so this here, I just added. I added W plus my minus V, which is W minus V. And there's the displacement. That's the difference. Displacement is right here. So that's just another way of looking at the subtraction, the difference. Okay. So we've got different components going on. Because remember I said we have a direction with vectors. So we have components of our vector. Okay. So here's a vector. Let's start here. Here. And I want to go, oh, for heaven's sakes. There. Okay. So and that's just, we went over 1, 2, 3, 4, 5, 6. So here is 6 if this was a number line. And I'm at 0, 0. And here is 1, 2, 3, and here's 4. Okay. So my vector, I can write U. Well, I went 6 units in the x direction, and I went 4 units in the y direction, but I need a way to specify that this is a vector. And so the way we do that is by this. Triangle brackets. So we have triangle brackets or pointy brackets or something like that. I just call them triangle. because I guess they sort of make a triangle. I don't know what their real name is, but that indicates I've got a vector, and it's telling me I've gone 6 units in the x direction and 4 units in the y direction. And that's if I use each square as a 1 unit, which seemed reasonable, so I may have to redo everything here. Okay, so we have special vectors. We have the I vector. Okay, I, so there's I vector. And I vector is 1, 0. So it's 1 unit in the x direction. We have the j vector, and that is 1 unit in the y direction. Now, that's in 2D, so in 3D, we would have 1, 0, 0, and j would be 0, 1, 0, and we would have k. So that's a j, and k would be 0, 0, 1. Okay, so it's a unit vector in a specific direction. All right, so on my little diagram here, this is I, right? 1 unit, and this is j, 1 unit in the y direction. And so a couple other things. If you've been in engineering and done vectors already, you might see the hat for the I and j. So that's fine if you use that, I hat, j hat, or k hat. Oh, no, not done on that, sorry. Right. So either of those is going to be fine. Now what this means is I can rewrite my u vector as separate components in each direction, and we would have 6 units in the I direction plus 4 units in the j direction. Okay. So that's a way I can write my vector in terms of component. I think the book calls it resolving. So we can write any displacement vector in 3 space as a combination of displacements in the coordinate directions. And your book, let's see, when you're looking at, a little too far. So your book calls this resolving when you're reading the book. So we resolve u into components by writing u in the form u equals u1 I plus u2 j plus u3 k. And this also equals u1, u2, u3. Okay. And u1, u2, and u3 we call scalars. And then it would be u1 I, u2j, u3k are called the components. So again, we use these special brackets because if you use, if you use U1, U2, U3 with rounded brackets, that looks like a point. Okay, where U1, U2, U3, and these triangle brackets means a vector. Is a vector. Let's just do that as a vector. Okay, so be careful how you label these because you have to be kind of clear. Okay, so now let's figure out how we do things, add some real vectors here. We got the idea. So now let's look at what would happen. So we're going to do component addition. Components. So we've got U equals U1, U2. V equals V1, V2. Right, remember you can write this as U1I plus U2J. This is V1I plus V2, V2J, right? Right, so U plus V in vectors, vector form. What we do is we add corresponding components. Okay. So we would get U1 plus V1, comma, U2 plus V2. That's what we do. KU, so a constant or lambda U, I just decided to change, right? So this is just going to be K times U1, comma, K times U2. Right. Let's see, minus U, so K is just -1, right? So you'd get minus U1, minus U2. The 0 vector is 0, comma 0. Okay. And we have certain properties. So let's write down all the properties. So properties. So U plus V is this. Goodness. This takes so long to erase here. So U plus V is the same thing as V plus U. Basically, you can add in any order. So U plus V plus W is the same thing as U plus V plus W in parentheses. U plus 0 vector is the same thing as 0 plus U is just U. Additive inverse. No, identity, something like that. U minus, here, U plus a minus U is just a 0 vector. Constants can be in any order, right? So you can have A times B times the U vector, and that'll be the same as A times B times our U vector. Or we can equal U vector times AB at the end. Either one. I mean, really, this is also the same thing as B times A times U, right? Scalars can be multiplied in any direction. A times U plus V is the same thing as A times U plus A times V, so you can distribute. A plus B times the U vector is A times U plus B times U. Again, you can distribute. Of course, 1 times U is just U. And those are the different properties. And I want to just look at a proof. A times U plus V equals AU plus AV. Okay, and that's what I'm going to start in the next video. Thanks.